Those who are online are able to see my screen?
Yes, sir.
Okay. So shall we get started? So tell me how to do the the problem 6.5. Let's make it fast, please. So 6.5, the question says, so for 6.5, the question says, a closed loop is held stationary in a magnetic field between north and south poles of two permanent magnets held fixed. Can we hope to generate current in the loop by using very strong magnets? The answer is no. How much ever strong magnet or magnetic field you are going to generate, right? You will not be able to generate any EMF in the conductor unless and until there is a change in magnetic flux taking place. Since they use the word stationary, so the value of change in flux is going to be 0. Since the change in flux is 0, EMF induced is also 0. Is that point clear? Right. The next question is, a closed loop, there is a closed loop, which moves normal to constant electric field, between the plates of a large capacitor. So there is a capacitor. So between the plates of a large capacitor. So when you talk about large capacitor, the electric field between it is going to be uniform. So when I take a conductor, the conductor is moving perpendicular to the electric field, right? Is a current induced in the loop? Is a current induced in the loop in the first scenario when it is wholly inside the region between the capacitor plates. Second is when it is partially outside the plates of the capacitor, and they have told that the electric field is normal to the plane of the loop. So means the loop is like this, electric field is in this direction. Question is there a current that is going to get induced? Answer is no. Why? Because for you to generate EMF, first thing is there should be a change in flux accepted, but what flux should change? It should be magnetic flux. Whereas in this question, they have told that there is electric field in the first place. So wherever you see electric field, that has nothing to do with generating EMF. Okay. So had they told, for example, there is a varying electric field in this problem, still, is there going to be EMF generated? No. What should change? Only magnetic flux should change. It has nothing to do with the electric flux. So magnetic flux is, the change in magnetic flux is 0. There is no magnetic flux at all in the first place. And the change obviously is going to be 0. Hence, there is no EMF induced in the coil. So when there is no EMF, there is no current, obviously. Am I clear with this point? Right? Right. So the third case is a rectangular loop and a circular loop are moving out of the region which contains uniform magnetic field. Right? Where are they moving? They are moving out of the uniform magnetic field into a region of free space. Right? And they are moving with a constant velocity v. In which loop do you expect the induced EMF to be constant during the passage out of the field region? In which of the cases do you think that the EMF is going to get generated uniformly? Is it in the case of a rectangle or is it in the case of a circle? It's the case of a... Answer is rectangle. Listen to this why. So I'm sticking to the same basic. I'm not going to change anything throughout this chapter. Listen to me carefully. If I want EMF to get induced, I'm going to stick to the concept saying that there should be a change in magnetic flux. So when I talk about magnetic flux, it depends on 3 parameters. What is it? It is BA cos theta. So I'm going to use this logic. One of the parameters among BA or theta will change and the other two will be a constant. In this case, if you see, the object is moving with a constant velocity in both the cases. So what is happening is, as this conductor is coming out, right? Since it's moving with constant velocity, equal distances are going to get covered in equal intervals of time. You can tell me, sir, the same thing is going to happen here also, because this is also moving with constant velocity and equal distances are covered in equal intervals. But it has something to do with the shape. In the sense, if this comes out, let's say this portion of the area is coming out of the magnetic field. See, this is the portion that is coming out of the magnetic field in 1 second. In the second also, the same amount of area will come out. What is going to happen? The same amount of area will come out. Whereas in this case, what will happen is, first, if this size comes out, in the second case, you might have this area coming out. And this area are not uniform. Are you able to understand? So for a rectangle, what happens is, the amount of the length and the width that is coming out, that is a product of the length and width, which gives you the area, is going to be constant. So to put it simple, the rate at which area is changing here is going to be a constant. I'll tell you why I wrote this. Whereas the rate at which the area is changing here is not constant. Are you in agreement with this? Are you accepting this? But why did I write dA by dt? Because flux is equal to BA cos theta. So if I differentiate on both the sides, I'll get d phi by dt is equal to, which parameters are constant? B is constant and theta is constant. So I can take out B cos theta outside. I will differentiate A. So it is going to give me dA by dt. So the rate at which the flux is changing is decided by the rate at which the area is coming out. So now read the question carefully, you'll be able to understand. In which loop do you expect the induced EMF to be constant during the passage? So this d phi by dt is what is EMF. So this EMF can be constant only if dA by dt is constant. So dA by dt is constant in this, whereas not in this. Are you clear with this? Clear? So that's the answer. Okay, make a note of it. Those who are online, are you able to understand the logic?
Yes, sir.
Yes, sir.
Good. உனக்கு சிலபஸ் முடிச்சிட்டாங்களா உங்களுக்கு? ஸோ 4th 5th எல்லாம் முடியல அப்ப. அடுத்து ட்ரை பண்றா. Shall I proceed? See, look at this one. See, just 2 important points. Listen to this carefully. In this chapter, if you're able to master Faraday's law and Lenz's law, right, if you're able to correctly find the polarities and everything, 90% of the chapter is over. I'm confident in telling you 90% of the chapter is over. The remaining thing is only applications of it. It's easy for me to put it in your mind. So concentrate and do it properly. If there is any doubt, get it clarified. So look at this problem. So predict the polarity of the capacitor in the situation described in figure 6.9. So what is happening here? There is a capacitor. See, listen to this very carefully. if I have a surface like this, right? If I have a surface like this, there are two ways in which you can look at it. See, if there is a surface like this, you're exactly seeing perpendicular to it, right? Right? If you're exactly seeing perpendicular to it, you will only be able to see a line. So this is basically a circular loop. So even if it is a circle or rectangle, whatever it is, if you're exactly going to look at it perpendicularly, you can only see the line. But if you want to see the circle in the shape of an ellipse, like how it is drawn here, there are two ways in which you can see. That is, you will either be able to see my palm or you will be able to see my knuckle. Right? Here, which one is correct? You're actually seeing the palm. How did I find out is, these dotted lines are there, no? If those dotted lines are going into the center, so this is the center of this loop, no? If these dotted lines are going towards the center, you're able to see that side. Are you able to understand? So it is like this means the coil is turned in this way. That is why you're able to see the center here. Had this dotted line entered from the other side, then the orientation would have been like this. It's a very, very important point to note. Am I clear with this? Right. Having said this, since the coil is like this, for this coil, you have B here and A here. B and A. Right. So when the north pole is moving closer towards the loop, what pole is getting generated? When you try to increase the flux, same pole. So when you try to increase the flux, the same pole is going to get generated. When you bring the south pole closer, what will happen? South will get generated. So since there is a loop, one side north, one side south is accepted. Okay, so what will happen is this will start acting like a magnetic dipole, as a result of which current is going to flow in which direction? Since you're looking at this side, see, since you're seeing this side, you're actually looking at the south pole. South pole means current should be clockwise. So clockwise means this should be positive, this should be negative. Current will flow across the wire first and then inside the conductor. So current flows from higher to lower potential is there? No, current flows from higher to lower potential outside the battery and lower to higher potential inside the battery. Are you able to understand? So A should be positive terminal and B should be negative terminal. Right. I think in your textbook, they have given it in the reverse. Check. Check what is the answer given there. There's new book, huh? Then it's so. Does anyone have old book? I think in old book it's given in the reverse. So A is positive, B is negative. Okay, then it is fine. So A is positive, B is negative. But did you understand the logic? See, it's problem wise ரொம்ப simple, rather. But the thing is, you need to understand how to look at the conductor. Can you just tell me for my satisfaction? When you look at a diagram, how are you supposed to look at it? Or coil இருக்குன்னா, how will you look at it? So first thing is, look where the dotted lines are entering. So if the dotted lines are going towards the center, that is the side you are able to see. So in this case, since it is happening on the right side, you are able to see this side. So which is your palm. When you look at it, so since this is going to be south pole, in your palm, the current is going to flow in the clockwise direction. When current flows in the clockwise direction, the current always flows from higher to lower potential. Where? Higher to lower potential outside the battery and lower to higher potential inside the battery. So that is why this should be positive and this should be negative. Is that clear? So though it is a capacitor, I'm using the word battery because I treat it like a temporary battery. Clear? See, just a slightly higher order thinking point. Listen to this carefully. Listen to this carefully. Had they twisted the question and told that the south pole is going to move away. Listen to my point. This is clear, no? No confusion. Right? What is happening? One side north, one side south. Suppose in this question, they told that the north pole is moving closer and the south pole is moving away. Then what would have happened? This will be north. This will also be north. So you cannot decide which direction the current is going to be. So you cannot say that how is the EMF induced in the coil. They mostly not do it. But did you understand? So for you to have this kind of a thing to happen, right? One of the sides should be North Pole and the other side should be South Pole, or else the current can never flow in a loop. You can ask me a question, sir. You are saying that from this side you're looking at it, it is going to appear like a south. It is appearing clockwise. So this side it should be anti-clockwise. No, still it will work. See, if this side it is anti-clockwise, this is A, this is B. The current is still flowing from positive to negative only. You look from whichever side you want, it will still work. So I'm just trying to open your mind. Okay, so don't think only from one direction. Think from all the directions. Is that clear? This is mostly important for MCQs and assertion reason based. You should have clarity in it. Am I clear with that? Shall I proceed? Right? Okay. So as I told, we'll do some more problems based on Lenz's law. It's very, very important question. So it is the first problem of your exercise. The first problem of your exercise. Still it will be the same. The kai irukilla, it is like this. That's what I showed. Either positive, either negative. Clockwise la suthudnu sonnam. Correct? So going from positive to negative this side. இப்போ இந்த சைடுல இருந்து பார்த்தா எப்படி இருக்கும்? இப்போ எப்படி சுத்துதுமா கரண்ட்? ஓகே, இந்த சைடுல இருந்து பார்த்தா எப்படி இருக்கும்? ஆன்டி கிளாக்வைஸ்ல தான். யூ ட்ரை அண்ட் see இது கிளாக்வைஸ்னா இந்த சைடுல இருந்து பாரு ஆன்டி கிளாக்வைஸ்ல இருக்கும். ஸோ இந்த சைடு நார்த் போல்ல மேட்ச். இட்ஸ் the same answer. Okay. Shall we proceed? So the first problem in this exercise is predict the direction of induced current in the situations described by the following figures from A to F. There are 6 diagrams. For those 6 cases, we need to find how the direction of induced current is. Right? So first look at it. South pole is moving closer to this loop. So since South pole is moving, South pole itself is generated. Right? So when South pole is generated, look at this diagram. Tell me, how are you seeing it? It is a circular loop. Your hand is like this. Are you seeing the palm or are you seeing the knuckle? So you're seeing the palm. So current should be in the clockwise direction. Clear with that point? But when it is going to be in the clockwise direction, so current in the first loop, observe the first loop, how it is. The first loop is having a jump, a hook kind of thing. It's saying that there is a disjoint hook, and the current is supposed to first enter Q and it will go to R, then come to P, then it will go back to Q. I'll tell you one common mistake that happens is when we say clockwise, no, most commonly people start writing the answer as PRQP. That is clockwise in the outside loop. Clockwise in this loop means once the clockwise part is completed, from the disjoint part, you see the diagram clearly. Where is the current first going to enter? It will enter Q first. So once it enters Q, from Q it should go to R, then it should go to P, then it should come back to Q. So the answer in this case will be QRPQ. So don't write QRP and leave it. Whatever point you started with, end with the same point. Only then it is a loop. Am I clear with this? Right? Now, for this case, so this is just an extension of this. So here we had only one loop, here we have 2 loops. So when the South pole is moving closer this side, you're going to have South pole here. South pole means again the current is going to be in the clockwise direction. So South pole clockwise means, look at the first loop. So where is the first loop going and joining? Look at the diagram clearly. It is going like this. Look at your textbook. No? Did you understand? So the first loop is getting connected to the next loop in the left of it. It is not getting connected to Q. See, had the current been in anti-clockwise direction, had it been north pole, the current would have been in anti-clockwise direction, then this loop would have joined Q. But the current, after completing the clockwise turn, so when you're looking from this side, it completes a clockwise turn, it goes to the subsequent loop, not to Q. So when it goes to the subsequent loop, first this current will reach the point P. After reaching point P, it will come to R, then it will come to Q, again go back to P. So what is the answer in this case? PR, QP. So current will be in the direction of PR, QP. Are you all convinced with this? Did you understand why is it so? See, when you see from this side, right, there's a coil, you're seeing the palm, right? So current is flowing in the clockwise direction. You have to check where, after completing a clockwise turn, where is the current entering? I don't know if I can zoom it here. I think the maximum zoom is also done. Understood? Unga textbook la பார்த்தா புரியுதா? Are you able to understand? So after completing the first loop, it is not entering Q. It is entering the next cycle. So after it completes every loop, it has to go to point P first. It has to go to point P. From P, it will complete R, Q, and then go back to P. That is for this wire. That is why it is PRQP. Right? Whereas when I talk about this wire, since the north pole is moving away, this side it is going to be south pole. Right? So this side it will be south pole, whereas on the other side it will be north pole. See, I am always comfortable looking at the palm, not at the knuckle, because that side is open for me. That will be easy for me to judge. Now, if you look at this one, no, the current is going to be in the anti-clockwise direction. Concentrate only on the first circle. Concentrate on the first loop. So when the current goes in the anti-clockwise direction, is it coming towards Y or is it going towards X? It is coming towards Y because there is a disjoint. There is a bend there, no? That bend gives you the hint of where the current is going to come out of the loop. So in this case, it will be YZ, XY. So it will be YZ, XY. Am I clear with this? Right? Okay. Now listen to this. So in the third case, right, you have a battery here, a positive terminal, negative terminal. You have a battery here where the current is able to flow in the clockwise direction. Which side are you seeing here? So the coil. Are you seeing the knuckle or the palm? Palm again. Right. So when you look at the palm, how is the current flowing? Clockwise. So this side is supposed to be south pole. Done. Now tell me one thing. Initially, when the switch is open, there is no flux associated with the coil. When there is no flux associated with the first coil, there is no flux associated with the second coil also. Right? Whereas, as soon as you close the key, tapping key just closed. So when you close it, the current is going to go from 0 to some value. So from 0, it is going to grow to some steady state value. When from 0 to I, the current is increasing, can I say magnetic field is increasing parallelly? Because current will generate magnetic field. Magnetic field will generate flux. So if the current is increasing, magnetic field is increasing. If magnetic field is increasing, flux is increasing. So if there is a coil which is facing a coil, if there is a coil which is facing a particular pole and the flux is increasing, what pole will get generated? Same pole or opposite pole? Same. So this side of the coil is facing a coil where the flux is increasing. So this will be south pole. So what will be the other side? It will be north pole. Why I wrote the other side is because the other side is also in such a way that you're able to see the palm. Look at the dotted lines. They're going towards the center in this side. Are you able to understand? So this side is north pole, means current should flow in the anti-clockwise direction. So what is the anti-clockwise direction here? YZ. That's the answer. It should be YZXY. Right? I want somebody to please check the answer at the back portion. Correct? For all the three, are they correct? Okay. This is slightly a tough problem, but it is very important. Concentrate. உனக்கு புரியுதாடா? அவனை கேட்கிறேன். உனக்கு ஃபர்ஸ்ட் புரியுதா? So இது பாருங்க. Look at this one. Those are online. Are you able to understand?
Sir.
Okay. So listen to this. The fourth one, right? It is a combination of conductor, coil, and rheostat. Okay. So this is where we need to be careful. You need to understand the principle of a rheostat. A rheostat works on the principle of R is equal to rho into L by A. So more is the length that is getting introduced, more is going to be the resistance. So if you look at this rheostat, right, it is something like this, right? It is something like this, which is connected to the coil. If this part is there, right? If this part is kept here, is more resistance entering this or less resistance entering this? It is more, because you are allowing the whole resistor to form a part of the circuit. Whereas when you move it this side, right, when it comes this side, what is it you're doing? You're decreasing the resistance. So using that logic, tell me, in this case, in this problem, are they decreasing the resistance or increasing the resistance? Had this blue color dot been here at the left extreme end, then you're saying that the whole resistor is a part of the circuit. Then resistance would have been more. So when they are moving it to the other side, they are moving it to the other side of the wire. Means they are cutting this part. So resistance is decreased. So when resistance is decreased, what is happening to the current? When resistance is decreased, what is happening to the current? It is increased. If current is increased, magnetic field is increased. If magnetic field is increased, flux is increased. So what I want to know is whether flux is changing. If at all it is changing, whether it is increasing or decreasing. I am answering only these two questions. Because I know the fact that if flux is increasing, same pole will get generated. Flux is decreasing, opposite pole will get generated. Clear with that point? Now tell me, for this coil, right? So for this coil, what you can do is, you can see from this side, you keep your hand like this, right? You keep your hand like this, and tell me whether you are able to see the palm or the knuckle. So in this problem, what I did is I use my left hand, right? In this problem, I use my left hand. That is why I told palm. In this problem, you can use your right hand, right? So when you use your right hand, again, you're able to see the palm. So when you see the palm, in which direction is the current moving? This one, this one. When you look at the palm, in the palm, the current at this point is going upwards, anti-clockwise. So current is anti-clockwise, means this side is north pole. So if this side is north pole and the flux is getting increased, this will also be north pole, right? So when I keep my hand like this, right? When I keep my right hand like this and look at it, Palm is there on the other side. So knuckle is there on this side. So on the side of knuckle, it is North Pole. On the side of palm, it should be South Pole. So for South Pole, what should be the direction of current? Clockwise means you yourself tell me. Why? That's the answer. It will be Y, X, Z, Y. There is anyone having confusion, please ask. Both are clear? Sure? Huh? Okay. Those are online, are you clear? Is there anyone having doubt?
No, sir.
Okay. So what about case E? So what about this case? In case E, what is happening? So you want to use your left hand or right hand here? Left. Okay. If you use your left hand, this side the dotted lines are there. No, which side are you seeing? Again the palm. It is like this. Okay. It is in this way. When the key is just released, what will happen? Current will decrease or increase. See, when the key is closed, current is going to flow. Key is open. If I switch it off, this will also get off. So current is going to decrease. If current decreases, what will happen to magnetic field? Current decreases, magnetic field decreases, flux will decrease. So whichever side is facing this side should have opposite pole. First of all, I need to find out what pole that is. How will I do? So if you observe, how is the current flowing? The current is going first in the upward direction, then into the plane. So upward and into the plane. Which side? Oh, this side the key is there. Okay. So current is flowing in this way. So it is going at the back and then coming over. So correction, listen to this. So current is flowing in this direction. So it is going into the plane and coming out of the plane. So when you see from this side, it will be anti-clockwise, means it is going to be, so this side is North Pole. Since the flux is decreasing, what should this side be? South Pole. If this is South Pole, what should this end be? North Pole. What should be the direction of current? Anti-clockwise. So anti-clockwise means how is the current going to flow? It is XRYX. Because when you take it in the anti-clockwise direction, the first loop is carrying the current to the subsequent loop, not to Y. So it is coming out and going into the plane. It is going like this. Where? Which case? Yeah. So here, if you observe, the current is going from the bottom, but the first loop is connected to the second loop. It is going like this. So when the current starts flowing anti-clockwise, first the current will go to X, R, Y, and then it will go to X. So what is the answer? X, R, Y, X. Okay. So check the answer at the back. நல்லா இருக்கா? I think there is something tough in NCERT, இது ஒரு problem. Something, it's tough to explain also. And a diagram ஒழுங்கா கொடுக்கலாமா? So had it been a 3D view, you will be able to see it better. நான் அந்த பாம்பு நக்கல்லாம் வச்சு நானா கண்டுபிடிச்சது. அதான் சொல்றேன். ஒழுங்கா கொடுக்கல. That is a problem, but try to understand. Okay. Now, the last one is this F. So current is flowing through this conductor and current is increasing at a steady rate. So when current is increasing, what will happen to the magnetic flux? Magnetic field will increase. Magnetic field will increase the magnetic flux. Okay, current is decreasing. Okay, then correction. So last point we'll see from the beginning. So here, when I say that the current is decreasing, magnetic field will decrease and the flux will also decrease. Right? Flux is also going to decrease. Right? Listen to this carefully. Due to a straight current carrying conductor, what is the direction of magnetic field? See, this is a straight current carrying conductor. Using the right hand thumb rule, the direction of field will be perpendicular to it. Means you will get circular shape around it. So the coil is actually in the direction of magnetic field. Are you in acceptance with it? So irrespective of whether the current is increasing or decreasing, with respect to this current carrying conductor, the coil is there. No, the coil is in the same direction as that of the magnetic field itself. So if the coil is in this direction, with respect to a coil, how is the areal vector? So if this is the coil, the areal vector is perpendicular to it. So magnetic field is in this direction, areal vector is in this direction. So what is the amount of flux that is associated with this coil? So flux associated with this coil is going to be 0. So irrespective of whether current is going to decrease or increase, there will be no EMF induced in it, because the flux is always 0 because of the orientation of the coil. Is the point clear? So in this case, there is no question of EMF induced at all. Am I clear? Right? Yes. So check the answer. Correct? No EMF. No. What is the time? Done now. Yeah. See, this is one such tough problem. See, I'll not say the problem is tough. Actually, the diagram they have given is difficult to explain. Maybe they can bring in a slightly 3D view into this so that you will understand it better. Right? But I hope you could get this problem. So if this comes in exam, you will be able to handle it. Let's see. So let's do this. 6.2. Use Lenz's law to determine the direction of induced current in the situations described by the figure 6.19. Okay. First is a wire of irregular shape turning into a circular shape. So there is a wire of irregular shape. It is turning into a circular shape. So what is the change that is taking place? Flux is equal to BA cos theta. So B is into the plane, constant. Theta is constant. What is changing? Area. So is the area increasing or decreasing? So if the area is increasing, what will happen to the flux? Increasing. So area increases, flux also increases. If there is an increase in flux taking place, it should generate the same polarity. So I've told you how to handle these problems. Whenever you have these kind of problems where the magnetic field is into the plane or out of the plane, consider what pole you are. So since here there is an into mark, this board is acting like the south pole, because south pole receives the magnetic field and we are acting like the north pole, right? So when flux is increasing, the coil should generate the pole which it is facing. The coil is facing us. Since we are north pole, since flux is increasing, what pole will get generated? There will be a north pole on the side which is facing us. Since it's north pole, what should be the direction of current? Anti-clockwise. Anti-clockwise means it should be A, B, C, B, A. A, B, C, B, A. Is that clear? So it should be A, D, C, B, A. So please keep checking the answers at the back. என்ன கொடுத்திருக்கும்? DCBAD AD ADCE இதுக்கா 6.2 ADC அப்படி Is that the answer given at the back? ADCD. அது லூப்பே கிடையாது. அது printing mistake வராது. I think there is a printing அப்படி flow ஆகாது. It is actually ADCBA. இப்படி current இப்படி போயிட்டு திருப்பி வராது. Then there is no pole at all. அப்படி இருக்காது. So there is a mistake. So it is actually ADCBA. ADCBA. சரியா? Right? Shall I proceed to the next one? Listen. So in the second case, a circular loop being deformed into a narrow straight wire. So initially, what was the area? It is pi r square. When it is getting converted to a narrow straight wire, its area is decreasing. So in this case, how will you observe? Flux is equal to BA cos theta. So A is changing. So since A is decreasing, flux will decrease. So since flux is decreasing, opposite pole should get generated. But listen to this. It's not south. Because here, the direction of magnetic field is reverse compared to this scenario. So it is out of the plane. So out of the plane means you are looking at the paper. See, for example, you are solving it now. You are going to look at the paper, no? So from the paper, the field is coming towards you. So what pole are you? We have the tendency to receive the field. So we are south pole. So since we are south pole, what will happen here is since the flux is decreasing, so there should be a north pole that is getting generated. So when it is going to be a north pole, what will be the direction? Anti-clockwise again. So A dash, D dash, C dash, B dash, A dash. I'm taking this loop. I'm taking this loop. Or you can write it as AD, CB, A also. Am I clear with it? Am I clear? So is that the answer given at the back? AD, CB, A or A dash? I hope you guys could understand, right? So as I told you, if you are able to master this, 90% of the chapter is over. So maximum 3 more classes will be done with this chapter. Chinna chapter. Seriya. Okay. So till now we saw the problems that are based on Lenz's law, right? So we'll do one last problem for today's session, okay, which is based on Faraday's law of electromagnetic induction. So the question is, a long solenoid with 15 turns per centimeter. So small n is equal to 15, right? It is 15 turns per centimeter. So everything is in terms of, okay. So 15 turns per centimeter means 1500 turns per meter. I'm converting everything to SI unit. 1500 turns per meter, that is the value of small n. So area is equal to 2 centimeters square, which can be written as 2 into 10 power minus 4 meters square, right? So there is a small loop of area 2 centimeters square, which is placed inside the solenoid normal to its axis. So if this is a solenoid, right, let's say this is the axis, there is another coil placed normal to its axis in the sense the magnetic field due to the solenoid and the aerial vector of this coil are in the same direction. So when a coil, listen to this carefully, when there is a coil placed in the direction perpendicular to the axis, okay, this is the axis, there is a coil placed in the direction perpendicular to the axis, then B vector and A vector of the coil are in same direction. This is a very, very important point to be noted, because when we see the word normal, no, first thing that we'll think of is theta is equal to 90. You'll think there is no flux. Don't make that mistake. Coil normal to the magnetic field means angle between B and A is 0. Okay. So if the current carried by the solenoid changes steadily from 2 ampere to 4 ampere in 0.1 second, So current is changing from I1 is 2 ampere and I2 is equal to 4 ampere. Just give me a minute. See, I1 is 2 ampere, I2 is 4 ampere, and delta T is equal to how much? 0.1 second. What is the induced EMF in the loop while the current is changing? So EMF is equal to delta phi divided by delta T. I'm only taking the magnitude. So when I talk about phi, right? Phi is equal to how much? Phi is equal to BA cos theta. What is the value of B? B is mu naught N into I. So here, because the current is changing, which parameter is changing? Magnetic field is changing because magnetic field is directly related to current. Am I clear with that? So mu naught into N into I into area into cos of how much is the angle between the magnetic field and area? 0 degree. I told this already, right? So it is going to be mu naught Ni into A. So what is the change in flux? So change in magnetic flux is equal to mu naught N into A. I will take it out because they are constant for both the scenarios. What is changing? I2 minus I1, right? Does this make sense? So mu naught into N into A into I2 minus I1 divided by delta T. So divided by delta T is going to be, okay, I'll write it as delta T only. This is what is EMF. So mu naught is how much? 4 pi into 10 power minus 7 into N is how much? 1500. So 1500 into what is the area? 2 into 10 power minus 4 into I2 minus I1. 2. The whole divided by time is 0.1. So 0.1 is 10 power minus 1. Right? So if you take this to the numerator, what are you going to get? 2 into 2 is 4. 4 into 1500 is 6000. 6000 into 4 is going to be 2400. So 2400 pi into 10 power minus 7 into 10 power 1 is 10 power minus 6 volt. Or it is 24 pi into 10 power minus 4 volt. Is the point here? Right? I forgot this minus 4. 1 minute, 1 minute. There is a small correction. So 2400 pi into 10 power minus 7 into 10 power minus 4 is 10 power minus 11. So 10 power minus 1 will go to the numerator. It will become 10. So 10 power minus 11 into 10 is 10 power minus 10 volt. Clear? Right. So okay. The next class I will start with mostly. Simple concept only. So after that is over, then we'll have self-and mutual preference. Those who are online, I hope you could understand.
Sir.
Yes,
Okay.
sir.
Okay, we'll wind up with this.